Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 5, VMware ESXi of the SQL Server on VMware Accelerator course. We just wrapped up a good overview of the physical server portion of this bootcamp. Module 5 covers our hypervisor, VMware ESXi. Traditionally, the hypervisor is a mystical black box that we never get access to or input into how it works. Let's learn more about what goes into that hypervisor and the things that we can do to make it run better. In this module, we'll be covering the basics of what a hypervisor actually does, and then go into some specifics on the VMware hypervisor itself. We're going to study the mindset shift that accompanies hypervisor management, including compute resource distribution and hypervisor resource scheduling queues. We'll also talk about what happens when these queues start to stack up. We'll then get into the specifics around how to set up a VMware ESXi host for optimal performance for your critical SQL servers. We're going to spend a good amount of time specifically on storage presentation, as there are a number of defaults that are quite substandard when you're running fast storage. Just like we talked about in the first module, traditional servers are generally underutilized. You have a physical server with an operating system installed on it, and because you purchased the equipment with enough spare compute capacity to run this workload through the end of its hardware life, or just overbought it in general, this server is usually significantly underutilized. Virtualization is the act of allowing multiple contained operating systems and whatever is installed and running inside them to run together on the same physical server. They're isolated in nature and do not know that the other virtual machines exist. What this usually allows us to do is to make better use of that physical server by consolidating multiple workloads together. It helps us cut down on the number of physical servers that we need to buy and maintain. VMware started the modern hypervisor trend, and as a company has been around for quite some time. In May of 1999, VMware Workstation was released. It allowed you to run a virtual machine on a workstation, and it was revolutionary. I discovered it in November of '99, and it changed my world forever. Yes, I am that big of a geek. In 2001, VMware released their first server-grade product, hosted on a regular OS through the GSX product, and hostless through the ESX product. In 2003, vCenter was released as the master controller behind multiple hosts and allowed you to run these together as one group of physical machines. vMotion was also introduced so you could move a virtual machine from one physical machine to another while it was running, usually with no disruption. It was also when the ability to create virtual machines with more than one virtual CPU assigned to it was created. In 2010, VMware released a major update to the product and called it ESXi. With ESX, the hypervisor operating system was much larger. What some integration companies had started doing was installing large programs inside what was called the service console, and these programs started to interfere with the way the hypervisor was actually able to stay stable and run efficiently. VMware stripped down the console and made it impossible for these companies to run large programs inside it. It was their way to lock it down to maintain product quality. One of the more recent releases was version 6.7 and was released in 2018. Version 7.0, the current release at the time of this recording, was released in 2020. Chances are you're probably running one of these two versions. If you're running older versions, you should definitely push your VMware administrators to upgrade to a more modern platform. Now, my history with running SQL Server on VMware goes back quite far. I was fortunate enough to have discovered VMware in November of 1999 when I installed a copy of SQL Server 6.5 inside a Windows NT 4.0 virtual machine on my desktop workstation. It was absolutely amazing. I had everything in a large production environment virtualized starting in 2004, including 6 large SQL servers. Since then, I've been working directly with VMware Corporation on a number of SQL Server virtualization initiatives and have been assisting in updating the SQL Server on VMware Best Practices Guide for over 10 years now. VMware ESXi is the modern hypervisor from VMware. Technically, it's a Type 1 hypervisor, as it is its own basic operating system, and you cannot run other applications on this platform directly. A Type 2 hypervisor is where a hypervisor is running inside a regular operating system, and you can do other things with that operating system. Microsoft's Hyper-V role running on an existing copy of Windows Server or Hyper-V or VMware Workstation running on your laptop falls into this category. If you just run ESXi as a standalone hypervisor host, VMware allows free use of this hypervisor, which they just call hypervisor, just like Microsoft does with Hyper-V. If you run this in a centrally managed environment, like I'm sure most of you do in your production servers, there's a licensing cost associated with this hypervisor. It's currently licensed by CPU Socket. You can see screenshots of the console, which is not elegant in any way in its gray and yellowish orange background, but it certainly does the job. When you access the web-based management interface, it gives you much more statistics and management tools for your virtual machines. Like I mentioned in the first module, virtualization is nothing more than a collection of computer resources in the physical server, including CPU, memory, network, and disk, and queues inside the hypervisor to allow multiple virtual machines to share access to these compute resources. If you take a look at this pyramid from the bottom up, it starts to make sense. Your virtual machines and their workloads submit tasks to the hypervisor to do certain things on these compute resources. They do not know that they are inside a virtual machine. They think they have direct access to the compute resources and just simply don't know any better. These commands then get placed into the hypervisor scheduling queues, which the hypervisor then sorts out who's got priority and how to manage the requests. It makes it through the queues, and then the compute resource actually executes that task. Our goal is to minimize the time spent in the queue. If we can do this successfully, we can maintain bare metal performance, which means maintain quite a bit of performance, but pile on a sufficient amount of SQL Server workloads to make the best use of that physical server that we can. The physical compute resources are distributed to the virtual machines through individual resources allocated to the virtual machine configurations. You can see here the DB01 virtual machine contains 8 CPUs and 128 gigs of RAM. It has one 10 gig network adapter assigned to it, and virtual disks added for a combined storage consumption of 3.7 terabytes. The DB02 virtual machine only has 4 CPU cores assigned to it, with just 32 gigs of memory and 1.2 terabytes of storage. As you can see from the image on the left, the server these VMs are running on is one of my lab hosts that contains 24 physical CPU cores and 384 gigs of memory. That gives us plenty of compute resources to allocate to other virtual machines. Maximums and limits do exist with the physical compute resources that we allocate. The physical server only contains so much of each compute resource. The physical host only contains a certain amount of gigahertz of CPU power, gigabytes or terabytes of memory, and network throughput to connect to other machines. Virtual machine maximums always exist, with caps to the number of virtual CPUs, number of virtual disks, or other caps. Now these ceilings are quite high, but they still do exist. There's also storage speed, which is more dependent on your storage subsystem and your interconnects than the physical machine itself. But we have to worry about things like the maximum performance available per LUN or the amount of demand that can be placed on the storage controllers before performance starts to degrade. The fun part of each of these limits are relatively easy to monitor and respond to. These are all items that system administrators have been monitoring for decades. If we look like we're about to run out of something, we can set tiered thresholds and alerts and respond accordingly. As you can see from this diagram, every single physical server resource has its own scheduling queue. If the time spent in that scheduling queue is low and everything is fine, if any of the queues start to stack up, everything being placed into that queue is going to suffer. This is one of those areas that is very difficult to predict, and if something happens to just one VM, lots of VMs on that host can be indirectly affected. Compared to the straightforward task of monitoring our resource limits, monitoring our queues become much more challenging. Some of them are relatively straightforward, such as memory pressure. Memory oversubscription should never happen in virtual SQL Server environments. Let me give you an example of this that I see quite normally in larger environments. Let's take the scenario where a physical server contains just 64 gigabytes of RAM. For round number's sake, let's assume that we're running a normal non-SQL Server workload with 10 virtual machines, each assigned 10 gigabytes of memory. Normal servers do not normally use all of their memory. Let's assume that the average virtual machine is consuming just 30% of its memory. That gives us 100 gigs of memory allocation, but just 30 gigs, or 46% of the host memory use. So far, so good. This memory oversubscription is not a bug or directly a problem, but it's actually a feature of the hypervisors. Your virtual machine administrators are quite used to managing virtual machines this way. Where things get into trouble is when certain things start to stack up. Let's say that on Friday evening, our weekly backups are all set to start at the same time. The backup program for this operating system consumes a small amount of memory running in each virtual machine. The average memory consumption per virtual machine then grows from, let's say, 30% to 51%. Our host is now consuming 80% of its memory, which puts us into a warning threshold. We don't have much more headroom on this host until we will be in a memory pressure state. Uh-oh, someone is working late and running end-of-the-month reports that happen to use memory on a few of the virtual machines. The consumption of these virtual machines then grow and consume 100% of the memory available on the host. These virtual machines do not know that they have pressured the host into running out of memory. The situation is now critical. The hypervisor then attempts to steal memory from some of the virtual machines to give it to the other virtual machines that are demanding more RAM. As a result, everything on the host slows down. This is not a situation you want to be in. Thankfully, this situation is quite preventable for our SQL servers as long as it's managed properly. The CPU scheduler is much more difficult to predict and detect, as our SQL servers are much more variable in nature. When you put many of these on the same physical machine, we can have random spikes in performance on any number of the machines, and if the queue scheduling is not well managed, it can result in a variable amount of performance penalty that your virtual machines can encounter. Go ahead and double check your ODBC driver name, as we're going to need this. We're going to launch HammerDB. It is a SQL Server and other DBMS platform benchmarking tool. To use it, double click on SQL Server. We're going to do TPCC. Expand out the little tree. Go to Driver Script option. Type in the name of the SQL Server you're looking to go test here. Check TCP. Change the name of the ODBC driver to match. Now Windows or SQL auth, no big deal. Timed script, we're going to go a 60-minute test here. Make sure to test all warehouses so we can really push it pretty hard. Go to load. Now go to virtual user, double click options. We're going to do 16 virtual users with a user and repeat delay of 50 milliseconds. Do not show output, it will slow you down. Hit create, then hit run. And the test has started. Now we want to see our transaction counter graph. So there's a not so intuitive button up top right here called Start Transaction Counter. Click on that and then give it a little bit of time. And you'll notice about every 20 seconds or so it's going to update with our transactions per minute rate. And this is measured live off a SQL Server. You can see this is a SQL Server that we're running against. It's a 12-core SQL Server, and that sucker is active. This benchmark is pretty aggressive. It'll throttle and slam pretty much any server you throw it at. So we're averaging about 180,000 transactions per minute. So not bad. Now, I'm going to simulate a synthetic workload in the background by ripping a DVD that I just happen to have. This is basically going to simulate activity. Now this VM is quite large. It's going to rip on just about all CPUs on this host. We're going to start the encoding. You'll notice it's a 24-core host. This virtual machine that we're doing the ripping on is 22 cores. That's pretty aggressive. We're going to fill most of the host here. Now, you notice we were at 180,000 before. We've dropped all the way down to about 120 to 130,000, and it stays there. Now, you'll notice the CPUs have taken a small hit here because of the amount of congestion going on in the background. This is your hypervisor resource time slicing and queue management going on. Now we're leveling out about 110, 120,000 transactions per minute. That's about a 35% hit. We're going to hit stop and let everything kind of reset and go back to normal. So you can see the processing is canceled, that is done, and over time, watch this sucker climb right back up. Now this is kind of an average since the last time it started up, so it's not going to go all the way back up. That is an aggressive simulation of what happens when somebody runs a noisy neighbor scenario. So end of month reporting, BI processing going on, ETL, just a lot of activity in the background. You saw that was good for about a 35% net performance hit to that SQL Server, and that is silent. You're not going to be able to find almost any traces of why that is occurring inside this virtual machine at that time. If you stick around to the performance module, I'm going to give you a few perfmon counters that you can use to actually sample a couple of things that VMware puts in there that you may not be aware of that will actually tell us that there is this level of stuff going on in the background. So stay tuned. Generally speaking, the virtual machine administrators do not have the time to micromanage these workloads. As a result, they usually just look at the host level for performance metrics. You can see on the screen here that it's using most of all of its memory, but our CPUs are quite lightly used. This image does not tell us much of what is going on inside the hypervisor, but this is usually where the virtual machine administrator stops because they are simply pressed for time and don't have the ability and time to micromanage these servers. They might even just be watching the maximum limits of the virtual machines and know that they're well within the confines of these maximums. The maximum values are amazingly high. At the time of this writing, a host can have up to 16 terabytes of RAM and allocate up to 768 virtual CPUs per virtual machine. The physical machine can also have up to 768 physical CPU cores as well, and there's only one manufacturer out there that makes a machine this big. We can have 1,024 virtual machines per host and assign up to 32 virtual CPUs for every physical CPU core. We can have VM host clusters as large as 96 hosts in a cluster, even though I don't think I would build them that large. These limits are incredibly high, but are still limits. I just wanted you to be aware of how large a virtual machine can actually scale. Not that you should do this unless you actually need it. Now we're going to get into some of the specifics on the virtual machine that are both applied to performance and streamlining the management of these hosts in the event that something goes wrong. We're going to talk through the power profile, similar to what you would normally do in Windows today, Syslog for error log collection, time synchronization challenges that could impact your SQL Server high availability solution, and then storage and virtual network presentation. The first thing to check at the host is that the host power policy settings are set to high performance. By default, VMware sets them to balance, just like Windows. You remember from the physical machine module where I told you to set the physical machine firmware CPU profile to high performance? Set the power policy inside VMware to high performance as well. This will forcefully eliminate any power savings that the host might try to impose at the detriment to your performance. This change can be done without a reboot or a host outage. The next is with time synchronization for the host. There are situations which I'll talk about in the next module where the virtual layer will attempt to synchronize the time inside the virtual machine with the time set at the host. If this time is not very closely in line with what Active Directory is sending, we may have an issue where a host's time differences to the virtual machine time may interrupt or even break our SQL Server high availability solution. Make sure that your system administrators have properly set up host time sync settings on each host. The diagram here shows using an external NTP source for time synchronization. Some organizations have an appliance inside their environments to synchronize to. Wherever you sync to, make sure it's accurate and up to date. Have you ever contacted Microsoft for a problem and the first thing they want you to do is send them the error log? The same thing happens with VMware. The challenge with ESXi is that since the installed hypervisor is very small, they keep the space to an absolute minimum. Error logs on each host are actually written to a temporary location and have a high likelihood of being erased at the next host reboot. If the host were to fail, these logs can be lost. Because we want to minimize the impact if there are any issues at the host, and this includes for your SQL Server host, we need to put these logs into a location where they're easy to fetch, even if a host goes down. We can specify two different means to do this. The first method that I recommend is to specify a data store with a folder on it for each host to write its logs to. Set it at the host Advanced Systems Settings screen with a parameter for the data store and then a path to a folder on the data store underneath in the settings syslog.global.logdir. All of the host logs are mirrored onto this data store as they change, and if the host fails, these logs are no longer lost. They can simply be packaged up and sent over to VMware for future analysis. The next is with a Syslog collector. A Syslog collector is simply a means to transmit log entries on an ongoing basis through a UDP stream to a central server for collection and analysis. Your infrastructure team should have one of these in place right now, and I won't get into any marketing on existing ones out there. I'm actually pretty impartial to which one you use, as long as you use one. Make sure one is configured here and validated prior to you actually needing this during an emergency. The next thing to verify is pretty straightforward. It's simply making sure that all of your network adapters that are in use by your virtual machines are redundant per virtual switch. This is generally a no-brainer for your VM admins, but it's worth double checking. Redundancy is critical here because if a network adapter or a cable were to fail, this provides seamless redundancy without an outage to any of your servers. We set redundancy here, so we don't always have to worry about network redundancy inside your virtual machines themselves. We've spent a lot of time on storage already, and unfortunately, the virtual environment tends to complicate storage even more. VMware has a number of storage adapters for block-based storage devices. These can include the virtual adapter for physical HBAs, fiber channel over Ethernet adapters, NVMe over fabric adapters, and any hardware or software-based iSCSI connections. Any of these adapters will have port bindings to pair with the physical hardware equivalent. You might have physical network adapter redundancy, but if you do not tell the storage layer how to enforce this redundancy and use all available paths to storage, it may not actually use more than one component. Your VM administrator should know how to configure these properly based on your storage configuration. The easiest way to double check this is with a storage test to see if you get sustained throughput equal or greater to what one path allows. If you're running iSCSI based storage, double check with your vendor for some of the advanced options that are present here. Many times the storage vendors will ask you to change certain settings, such as login and logout timeout, or a word setting called delayed ACK. Your storage team and VM administrators should confirm this, so just ask them to make sure they follow all the guidelines from your storage vendor. Any of these block level devices will present a LUN to your physical machine. The hypervisor layer will see this as locally attached storage, even though it is shared amongst all the hosts in the cluster. The hypervisor then formats it as a data store with a clustered file system, and now you have a data store that you can place your virtual machines onto. Once we start to really drill into the storage presentation, there are additional settings around active multipathing so that a host can actively use more than one path to get to your storage. This is called the Path Selection Policy, or PSP. The preferred PSP is round robin. Your storage vendor might actually have utilities or just scripts that will help enforce this. If you're poking around your VM platform and see that the multipathing policy path selection is set to something other than round robin, double check with your VM administrator if this is set properly for your storage. Now, the round robin policy is not perfect. It will have some rather interesting thresholds built into it. By default, all virtual machine traffic on a host will traverse just one path until the IOPS demand exceeds 1,000. At that point, the next virtual machine to request a storage operation will flow onto the second path. It does not mean that one virtual machine can use more than one path to access storage. For example, two 10 gigabit network adapters in a default configuration does not mean that we will get a single 20 gigabit worth of throughput for a single virtual machine. One virtual machine will be capped at 10 gig of storage speed, and the next VM would be able to consume the remaining 10 gig. Thankfully, we can adjust this. Sometimes your storage vendor may have a special multipathing plugin that can aggressively use all storage paths for an individual virtual machine. Most of the time, they don't, so we can override the default setting to set what is called round-robin IOPS threshold to just 1. Changing the setting will force the virtual environment to flip-flop between all available paths, and effectively multipath all available storage paths for any and all virtual machines on that host. See the link on the screen at vmware.com for more details. When in doubt, check with your storage vendor if changing this setting is needed or supported. Most that I'm aware of are fully supportive of this change, but you never want to take any of that for granted. I spent a lot of time in the last module discussing the physical HBA or storage adapter queue depth. If you've made a change to that setting, you will need to make an equivalent change to the VMware driver inside of each host. Check with your specific device manufacturer for the mechanism to make this change. There are plenty of examples at the VMware KB article on the screen, and changing this is usually straightforward. Changing the setting does require a host reboot, so do this before the host goes into service to make your life easier going forward. If you're using software-based iSCSI, your default queue depth value is 128. On most arrays, this setting is just fine. If you're using an all-flash or NVMe storage array, this value can be increased to improve your queue depth and make better performance under heavy load. As always, check with your storage vendor for their recommended settings, but I find that for good flash arrays, you can usually double this setting with some pretty good effects. That's not the only layer of storage queuing that we have to worry about. We've now tuned two different layers. Let's introduce a third. There's a setting called DSNRO, or disk.sched_num_rec_outstanding. Say that 3 times fast. Let me translate this one as it's a little nerdy. In VMware lingo, VMware defines a world as a single virtual machine and its connected disks. I guess they're the center of their own universe or something. If only one world exists on a data store, the queue depth at that host to that data store is inherited from the queue depth maximum on that virtual machine's storage configuration. However, if more than one world exists on a data store, which is very common, the queue depth of that data store on that host is limited to just 32. Think about all the queue depth changes that we've made for fast storage up to this point. That queue depth is much higher. This default queue depth limitation of just 32 can cause an immediate storage bottleneck for any and all of your demanding SQL Server virtual machines. Thankfully, you can adjust this higher as needed. If you're on flash hybrid or all-flash storage, I recommend testing increasing this value. More detail is presented at the link on the screen. I can tell you comfortably that this particular setting is at the root cause of many storage problems in virtual environments. Thankfully, when we get to the performance module, I will show you some key metrics inside VMware that we can monitor to quickly detect if these queues are starting to act up. Network presentation of storage gets a lot easier. The share on the storage is mapped as a data store to each host, and that becomes a data store where we drop our virtual machines onto. On the VMware platform, this is done through the Network File System Protocol, or NFS. Think of this as a Windows share, but for the Linux and Unix platforms. Depending on your storage subsystem, you might have NFS version 3 or 4 available to you. NFS version 3 does not actively multipath or allow you to use multiple physical network adapters for a single connection to the storage subsystem. If your storage teams want to multipath this architecture, they will need to perform advanced networking to bind multiple interconnect paths together to form a single presented faster connection. NFS version 4 does allow multipathing if it's set up right. Test your multipathing ability and work with your storage vendor to make sure that everything looks good on their end. You can test multipathing quite easily from within the virtual machine if you run a storage test or some other storage demanding operation and get greater throughput than what one physical network adapter provides. There are some tuning opportunities here, and check with your storage vendor to make sure that everything is set up right. I do find that many of the settings that you see on the screen here can be tweaked per your storage vendor's recommendation to provide a little bit better performance. See the KB article on the screen for one in particular that I find that makes a pretty good difference with the receive ring size. There is a really cool feature for virtual environments that allows a virtual machine to be migrated from one physical machine to another while it's running with no disruption. VMware calls this feature vMotion. Since this is shared storage, the storage stays in one spot, and the host copies the contents of memory from one host to another. Once the changed memory blocks reach 0, then the virtual machine networking pointer is switched over to the second host, and now the virtual machine is running on the second host. You can usually do this without any disruption on the SQL servers. Sometimes, if you're running a constant ping during the vMotion, you'll see one loss of a ping. This is quite normal during the point in time when the virtual environment swings the network pointer from the first host to the second. Normal applications will treat this as a TCP retry operation, and no interruption is encountered. The challenge here is that since we're copying the contents of memory, some of your SQL servers have some really large memory footprints. The time spent copying this memory footprint can seem to run quite some time. Thankfully, VMware does have some advanced settings that we can tweak to improve the performance of our vMotion operations, which reduces the time that it can take to perform this operation. It's called Multi-NIC vMotion. Normally, by default, even if you have more than one network adapter assigned to the vMotion process, it will only use one. The network adapters can be assigned in a certain way to tell the hypervisor to actively multipath the vMotion memory stream and speed it up. Your VM admin should know how to set this up. One VM kernel port group is set up for each of your physical network adapters. For each one of these, one adapter is set up to use the active adapter, and the rest of the NICs are set as standby or unused. If all of these network adapters and components are actively mapped properly, the hypervisor will then use all available network adapters to simultaneously push the vMotion contents. For example, if two 10 gigabit adapters are used in this configuration, we cut our vMotion time in half. If we take the concept of jumbo frames that we talked about in the networking module and enable them for the vMotion network, we're able to get up to a 30% gain for vMotion operations. Thankfully, this is pretty straightforward to set up for just this network. Every little bit helps, and the combination of multi-NIC vMotion and jumbo frames can help us decrease our vMotion runtimes by up to 2.5 times or more. That's pretty substantial when we need these operations to be done in a hurry. Remember those VLANs in a previous module where I talked about network segmentation? The virtual machine network assignment corresponds to the networking segment and usually VLAN that were created by your virtual machine and network administrators. Many times the virtual machine networks are created on each host, but in larger organizations, the virtual network can be created once at the vCenter level through something called a virtual distributed switch, and then applied to all hosts in a cluster to make management easier. Work with your virtual machine administrators to make sure that your networking segmentation needs are met and that the appropriate number of virtual machine networks are created for you. Okay, that'll do it for the individual hypervisor. In the next module, we'll take a bunch of these hosts and put them together to form a VMware host cluster. Stay tuned.